this computer. Sorry. Okay. So can anybody tell me what negative 10 plus negative 45 is?
So that negative 55?
Yeah, absolutely. A lot of students will make the mistake of thinking that a negative and a negative make a positive, but that is only true in the context of multiplication. So you don't want to overgeneralize um, these rules that you may remember vaguely from grade school, uh, but you sort of want to apply them everywhere. Um, I would say you want to think about this more of like money. Like if I owed somebody $10 and then I went and borrowed $45 for them from them, I owe them a total now of $55. But because I owe them, it's going to be negative, right? Or another way of thinking about it is if I have negative $10 in my bank account because I've been a little bit of a shopaholic this month, and I end up going out and buying something that is $45, my bank statement should say that I owe the bank $55, right? And this is really nice. We have a property with addition that you might already recognize, but um, mathematicians have a special name for it, and it's called the commutative property. And that is that if you have a number plus another number, that you can switch the order and you'll get the same result. So if I tried to trick you by saying, okay, well, we know that this negative 10 plus negative 45 is negative 55, and then I ask you, what is negative 45 plus negative 10? What should the answer be?
Negative 55.
Yeah, negative 55. So we say that the commutative property works for addition because you can switch the order of that operation and it doesn't change the result that we get at the end. So this is a numerical expression, right? A statement that has numbers and operations, and you can get a single result. Okay. With subtraction, let's try something a little exotic as well. Let's do negative 10 minus 12. Does anybody know the answer to this one? Or what can we simplify this down to?
Minus 22.
Yeah. And you could reason it the same way with a physical interpretation. Like it seems whenever I tell students think about money, it just comes naturally. If you have negative $10 in the bank and you spend $12, well, then you should have negative 22 in the bank now. Or in other words, you owe the bank $22. But here, we would say that subtraction as an operation is not commutative. Because if I keep this as subtraction, but if I switch the order of the numbers, I put 12 minus negative 10, we'll see that the result here is actually going to be positive 22. And I'll put a plus here just to be really clear. Positive 22. Is anybody confused as to why this is?
Yes.
Okay, so what is the point of confusion?
Because you have 12 and then you're taking away 10.
No, I'm not taking away 10. I'm taking away negative 10. So the way you have to think about this is you have to sort of read it as clearly as it's written. 12 minus negative 10. And then we sort of need a better way to interpret that because it's sort of minus negative sounds confusing. Think about it like, okay, I have $12 this is implied to be positive because there's no symbol in front of it, right?
Right.
If somebody takes away your debt, right? We can think of negative values as debt. If somebody takes away your debt, like let's say Bernie Sanders takes away my my student loan debt, that's effectively the same as giving money, right? Like giving a positive amount. So whenever you see 12 minus a negative or a number minus a negative, you should more simply think about it as 12 plus 10.
So is that like a rule, a negative and a negative turns into a positive or something?
When you subtract a negative, it's the same as adding the positive.
Okay.
So, or you could think about if you take away debt, you're giving money.
Okay.
I'm sorry, Professor. Can
Yeah,
I
go
say
ahead.
something? So I took this back home, and okay, so when the positive number is bigger than the negative number, you always put the positive sign, right? Isn't it right? This is how we took it back home.
I think that you might be confusing a little bit with addition of signed numbers.
Mm-hmm.
In this case, like it doesn't really help us to say, okay, 12 is a bigger number, so it's going to take the sign of the positive. But I sort of know what you're saying.
I think you know what I'm saying, right? It's about like which it's okay.
Yeah.
I'm not trying to confuse you guys, but this is how we took it back home. So
That rule is for if you're adding numbers that have different signs.
uh-huh.
So if you're adding numbers that have different signs, let me go ahead and write an example of that. Right, so like even though I'm starting here just trying to briefly talk about addition and subtraction, we can see that there's already like where we think that, okay, well, I already understand how addition works or subtraction works. If we're not clear on these like ambiguous cases, then we're gonna have a lot of pain a little bit later on. So like here's an example that I'm not sure who is speaking right now, but
It's Robot Khatib.
oh yeah. So when you're adding numbers with different signs, let's say I have 23 plus negative 48. Then you have to think about, well, what is the result going to be in terms of positive or negative, right? What's the sign of the result here without doing the math?
Mm-hmm.
And in this case, what we're saying is that you look at the numbers here,
Mm-hmm.
regardless of the sign, which one is bigger?
The 48.
The 48 appears bigger.
Mm-hmm.
Mathematicians would say, well, technically negative 48 is a smaller number, but as a what do you call these? Rule of thumb. As a rule of thumb, you'll say, okay, just look at the number and ignore the sign. Which one is bigger? We would say
The
this one has
48. So
a
you would take
bigger absolute value.
okay, so you'd be taking the bigger number sign, basically. So it's gonna be
Yeah.
negative 25.
So this will be and because they have different signs, you're going to subtract. So 48
Mm-hmm.
minus 23 is going to give you your numerical result, which would be the 25.
Mm-hmm.
But because this is a larger value, your answer is really going to be this negative 25.
Yeah, the negative 25. I got you. Thank you.
Yeah. Keep the sign of the larger. But again, this is only, that rule only works, or that rule of thumb only works for adding numbers with different signs. And, you know, because we're here in college algebra, I have to assume that we know how to add positive and negative numbers. So I'm not gonna take too much class time to sort of rehash these rules. But when you run into those problems, what I want you to do is write them down and then visit me or one of the other tutors in Math World, just so that we can clear up those discrepancies, because they will haunt you the rest of the semester if we don't get them cleared up. Okay. So let's talk about multiplication and division real quick. I say real quick, but it really depends on how this goes, right? For multiplication, let's say we saw some of these problems before. 1/2 times, I don't know, let's do 4/7. And maybe I'll throw a negative in front of this one, just to complicate it a little bit. Multiplication, like I said, if we have a negative times a positive, we should be getting a negative. That is the rule for multiplication. A negative times a positive gives you a negative result. And it doesn't matter that this is a negative. The rule for multiplying fractions is going to be the same. We're going to multiply the top. We're going to multiply the bottom. And we're going to keep this negative sign. So this should be negative 4/14, which I could reduce down to 2/7. So this will be negative 2/7. Okay, and the commutative property also works for multiplication. That is, if I have some number, a times b, doesn't matter if these numbers are fractions, doesn't matter if they're whole numbers, it doesn't matter if it's positive or negative. If I have any numbers, any two numbers, and I switch the order of the multiplication, I'll get the same result. So just as an example, just to prove this, it's not really a proof, but just to give you some sort of assurance that it does work, 4/7 times -1/2. 4 times -1 is -4. 7 times 2 is still 14. So even though I flip the order, I still get this same fraction, which reduces to this same result. Okay, so with addition and subtraction, the order in which we do that addition doesn't matter. But with subtraction and division, the order does matter. So with division, we might have something like, let's just do something 9 divided by 1/7. I was going to say something easy, like 9 divided by 1/7. Well, we learned how to divide fractions last time, so it should be clear that we should change this to 9/1 so that we have this as a fraction. Switch to multiplication, and then flip this to the reciprocal 7/1. So this will just be 63. Ooh, which nobody can see. There we go. Okay. But if I'm going to say that this is not commutative, because if we change the order here, if I put 1/7 divided by 9, and I still use my same division rules for fractions, call this 1/7, leave that one alone, switch to multiplication, and then flip this one to its reciprocal, 1/9, I will get 1/63. And this is not the same as what we got before. Okay, so you always want to make sure that the rules are being applied consistently, right? You don't want to put your brain on autopilot and just say like, oh, okay, yeah, this makes sense. I get a result, so that must be the answer. You need to make sure that you can explain why it is you got to the result. If you cannot explain it, if you cannot articulate it, then, and I know this sounds mean, then you haven't learned it, right? Then you don't know what the answer, you don't know the process. So what I want you to like really focus on is like that the point of this course, the point of mathematics is not to just do something and then it spits out some answer and that must be the correct answer. I want you to be able to reason why you got to the correct answer, because that will help you in understanding what's going on, so that when we get to more complicated things, you'll be able to reason why, you're working on a homework problem and you just can't seem to get the solution, or your solution is off by a little bit and you're able to explain to yourself why you were wrong, right? We want to be able to explain why we're wrong as well as why we're right. Okay. So what we're talking about, because we got lost in the weeds a little bit there, I think, is numerical expressions. We have addition, subtraction, multiplication, and division. We're going to have to be pretty comfortable with those, because we have other operations that we're going to be applying in this course as well. Can anybody tell me what an exponent is? So at some point in maybe a previous math class, you learned multiplication as repeated addition, right? Like if I had 2 times 3, that's the same thing as 2 plus 2 plus 2, right? Like I have 3 copies of the number 2 and I'm just repeatedly adding them. So let's think about multiplication as repeated addition, where even 5 times 4, you could think of it as 5 times 5 times 5 times 5, right? Where I have 4 copies. I'm sorry, not times, plus. Well, now that's just ambiguous. 5 times 4 should be 20, so these should be addition signs. But I have 4 copies of 5, and I'm adding them. And this should be 20. Okay. Well, exponentiation is this idea that we want to be able to repeat multiplication. So exponentiation, whenever it's first introduced, is going to be introduced as repeated multiplication. But the notation can be a little bit confusing sometimes. So here's the notation. We'll write a number here. I'm going to write it as B. And you'll have a little exponent up here. I'm going to put an X. Okay. So we call this B because it's the base. And this up here, this number that's a superscript, that is, it's a smaller typeface, and it's raised in the upper right-hand corner of the base. The superscript is the exponent, but sometimes we call that the power. We say that we have a number raised to some power. And so as a concrete example, if I had 2 raised to the 3rd power, what this is actually 2 times 2 times 2. We're repeating that multiplication, but we have 3 copies of the base, 2. So this is just really a shorthand in the same way that multiplication is shorthand for repeated addition. So I would say that 2 to the 3rd power since I understand that this exponentiation is 2 times 2 times 2, well, this is going to be 8, right? If I were to simplify this. Does anybody have any questions, comments, or concerns about that? So you're going to need to proceed with caution, because if you're trying to rush through your homework or any problem that involves exponents, and you see something like 4 to the second power, it's very easy to say to yourself, oh, 4 to the second power is 8. But that's not true, right? That's a big mistake. Because you don't want to rush through it and say, oh, 4 times 2 is 8. What you really want to do is take your time with it and say that 4 to the second power is equal to 4 times 4. So 4 squared, or 4 to the second power, is equal to 16. Does anybody have any questions there?
No, sir.
Okay. One more thing is that I know I'm using a whole number as an example here. This is going to work for negative numbers and for fractions as well. So let me give you an example of a fraction raised to a power, right? We have 1/2 and an exponent of 3. So you'll have to remember, and you know, to solve this, we'll go ahead and write it out as 1/2 times 1/2 times 1/2. 3 copies of the base. So this 3 is being applied to everything that's in the parentheses. The stuff in parentheses is the base, so we write 3 copies of it and just multiply it out. On the top, when you're multiplying multiple fractions, you're just doing 1 times 1 times 1. On the bottom here, 2 times 2 times 2, which is going to be 8. So this will be your answer. Okay, let's look at a negative. Now the negatives, if I have a negative in here, I'm going to put a negative, let's say 2/7 raised to the third power. Well, I'll go ahead and apply that, the definition of our exponent, but this is negative 2/7, and I need 3 copies of this. So whenever I have a fraction and they're negative, I'm going to throw them in parentheses just so that it's less confusing. At least it is to me, okay? So I want you to be able to get comfortable with thinking like, okay, if this is going to be ambiguous, let me throw some parentheses and just, sorry about that, that's a 2, negative 2/7 there. And then we can multiply this out. 2 times 2 times 2 is going to be 8. But really this is negative times a negative times a negative. So negative 2 times negative 2 is going to be positive 4. So let's go ahead and do this one at a time, right? These two can combine to make negative times negative is positive. So I'm going to have positive 4 over 7 times 7 is 49. And then I'm multiplying that positive times this remaining negative. And I should be getting positive times a negative, which should be negative 8 over 49 times 7 is going to be a large number. So I'll just grab my calculator for that. 49 times 7. 343, and I'll call that a day. Does anybody have any questions about this one?
Let's just say it was to the fourth power, then would it be positive?
Yeah, absolutely.
Okay.
So if I had a negative, let me say 2/3 to the fourth power, then I'm going to apply the rule for exponentiation. I'm going to write 4 copies. So I might throw 4 sets of parentheses and then fill that in with my base, which is negative 2/3, negative 2/3, negative 2/3, and negative 2/3. So negative times a negative is going to be a positive. So you want to solve these in pairs, right? Or simplify them in pairs. Negative 2 times negative 2 is positive 4. So we have 4/9 right there. And then this pair will result in the same number, positive 4/9. And then we'll go ahead and multiply that out and get 16/81. And that's positive. Any questions there? This also works for decimal numbers. So if I had, for instance, 0.05 raised to the third power, I really honestly don't like messing with decimals, but 0.05, we're going to do 3 copies of that. And 5 times 5 times 5 is something like 125. So I know there's going to be a 125 in there, but I'm not sure where the decimal value is going to be. So I might go ahead and just throw this in the calculators. So 0.05 times 0.05 times 0.05. And I get this weird scientific notation. If you have this calculator, then let me see. You want to make sure that the mode is not in scientific, and mine is not. It's in normal mode. But if you have like just a phone calculator, let's see. Can you guys see this? I got the camera instead of the calculator. 0.05 times 0.05 times 0.05, 0.000125. So I'll put 0.000125, and I'll call that a day. Now you could do this by hand and figure out, where those decimal places go. It turns out that because each of these has 2 values, 1, 2, behind the decimal place. So 1, 2, 1, 2, 1, 2. Let me see. 1, 2, 3, 4, 5, 6. Yeah. 2, 3, 4, 5, 6. Something like that. If you were to do this by hand, you would have to move like, you'd have to do this 0.05 times each other. You'll get some result here. It'll be 25 when you multiply that out. And then the zeros won't multiply to anything else, but you'll have to move this decimal place. There are 4 decimal places here, so you'll move 1, 2, 3, 4 and get 0, 0, 25. And then you'll have to multiply that out again here. But I don't want to emphasize this process here. I want to say you're going to want to use the calculator for this if you're not clear on how to multiply decimals and where the decimal moves to. Okay. We could talk about that outside of class in Math World or during office hours, and that's just the way it's got to be. So I'm gonna move on. So the takeaway there is that exponents, that rule of repeated multiplication, you're just going to have to be clear on what the problem is saying, because we're going to run into exponents quite a bit throughout the semester. Okay. One thing that I do want to emphasize is the language in which we talk about exponents as we go forward. You're going to hear me say blah, blah, squared. Where blah, blah is going to be some number or some quantity. Okay. So whenever we say the word squared, at least mathematicians or math folks like myself, what we mean is that the exponent is the number 2. So as an example, if I talk about 3 squared, what I'm saying to you is 3 to the second power, which simplifies to 9. Or if I say 5 squared, it's sort of like math slang. We all know what we mean when we say squared. This would be 5 squared is equal to 25, because that's 5 times 5. And so on and so forth. Something squared is something multiplied by itself, or something raised to the second power. You might also hear mathematicians, tutors, and such say blah, blah, cubed. What we really mean is here is that the exponent is 3. So if I say 3 cubed, then that's the same thing as 3 to the third power, which would be 3 times 3 times 3. And that would be 27. If I said 5 cubed, that would be 5 to the third power. And that would be 5 times 5 times 5, which should be 125. Okay. So that's what I'm going to mean when I throw out this sort of math slang, just sort of casually say, okay, we have this quantity cubed, this quantity squared. We don't have any fancy terminology or slang for any other exponents other than 2 and 3. So that's just something to be aware of as we proceed through this. There are other operations in mathematics that we're going to run into here, like roots. Okay. So in our arsenal, we have addition, subtraction, multiplication, division. Now we have exponents, and we also have to be aware of roots because we're going to run into those. And roots are the inverse operations that correspond to some exponent. When I say inverse operation, I mean that the operations cancel out. Okay. Or they reverse each other. So let's just, as an easy example of this idea of inverses, think about addition. If I had $10, okay, and then I added $5 to that, let's say I found a $5 bill on the floor, and then I went and I bought a Starbucks coffee, and I said, keep the change, and that coffee was $5, and I spent that $5. Well, these operations that I've performed on my original quantity, this is my original. I perform the operation plus 5. And then I perform the operation subtract 5. These two operations cancel out in some sense, right? Because I'll be left with my original amount of money. So we say that addition and subtraction are inverses, because these guys cancel out. Another example would be, let's say I took $100 and I took that to the stock market or maybe the cryptocurrency exchanges, and I made let's say I doubled my money. So I multiplied that by 2. But then I left the money in the market for too long before taking out my earnings, my winnings, and then the market halved, and so I divided that money by 2. Well, it should be clear, in some sense, that this original quantity, I'm just going to call it OG, my original, got doubled. So I doubled it, and then dividing by 2 halves it. Not sure how to pronounce how to spell this one. Halves. But in any case, it performs multiplication by 2 and then division by 2, and those sort of cancel out because 100 times 2 is 200. 200 then divided by 2 gets us back to our original. So we can say that, in some sense, multiplication and division are inverses. Okay, well, it turns out that exponents have an inverse too, and that's this thing that we're calling roots. So let's think about this for a second. If I had 5 to the second power, 5 squared, I would get 25. And since we've already paired up addition and subtraction as inverses and multiplication and division as inverses, I want to introduce a new operation that will take me from 25 and get us back to the original amount being 5. So what operation could I do to 25 that I haven't done already that will take 25 and transform it somehow so that we're getting back to 5? Does anybody know?
Divided by
Square
5.
root.
So somebody said divided by 5, but we really think about multiplication and division as being inverses. We need to
Okay.
introduce a new operation so that we can transport this back to 5. And that operation is going to be taking the square root of 25, which gives you 5. Okay, so it turns out that squaring or raising something to the second power is inverses, or is an inverse of taking a square root. Have you guys seen this operation before, or this symbol?
Yes, way back when.
Yeah. Okay, so I want to talk about some roots here. about some square roots. So the idea here is that we want to think about some numbers as being perfect squares. That is, if I take a number, so here's my number, I'm going to make a little table. And I'm going to use the natural numbers 1, 2, 3, 4, 5, 6, and so on. And I'm going to apply the operation to this number. So I'm going to take this number and I'm just going to raise it to the second power. Right? Remember, the second power we would say that that is squared. Well, 1 times itself, or 1 raised to the second power, is equal to 1. So I'll box this in. And I'm going to do that for all of these numbers over here in this column. So I have 2 to the second power, 3 to the second power, 4 to the second power, 5 to the second power, and 6 to the second power. 2 to the second power is 2 times 2, which is 4. 3 to the second power is 3 times 3, which is 9. 4 to the second power is 16. 5 to the second power is 25. 6 to the second power, 6 times 6, which is 36. And so on. We call things in this column perfect squares because we have taken a number and we have squared it. So 1, 4, 9, 16, 25, 36, 49, 64, 81, and so on. Those are all perfect squares. Well, if you take your perfect squares, so your 1, your 4, your 9, your 16, your 25, and your 36, and then you perform this operation, the square root of your perfect square so the square root of 1, you would just get 1. The square root of 4, you would get 2. And so in some sense, the square root is asking you, the square root of some number is like it's asking you, what number times itself gives you the number inside the root. So if I think about this question, the square root of 4 is asking me, what number times itself gives me 4? So the answer to that question is 2. Okay. The square root of 9 is asking, what number times itself gives me 9? So that answer must be 3. What times itself gives me 16? That is 4. What times itself is 25? That's 5. What times itself is 36? That's equal to 6. So you can see that, let me just pick an arbitrary one here. 4 to the second power gives me 16. So if I take 4 to the second power and I get 16, and then I take a square root of that, then I get back to my original. So that's what I'm trying to illustrate here, that we have this new operation of exponents, and then roots are going to be corresponding to them that undo that operation. That's the opposite operation. It takes us back to our original number, our original value. Okay. Well, I know that I've probably inundated you with a lot of this like nuance of operations here. When are we going to get to some problems? Well, here we go. We're going to jump into the mix. I'm going to give you some problems that won't complicate your life too much, but we're working with numerical expressions. And these numerical expressions are not going to be these simple problems that I've given you where you just have two numbers and one operation in between them. We're going to get operations that, or numerical expressions that combine multiple operations. So we need to use, let's say, let's do this one. I put the number 6 here. Let's practice this. I'm going to call this number 1. Can anybody tell me what 11 times 6 plus 10 times 19 is? Now, you could probably throw this into the calculator, but I really want you to challenge yourself to do it without.
Is 57?
Let me see. What did you get again? Can you repeat your result? Or anybody else?
Sorry, I say it's 57.
57?
Mhm.
Can you tell me how you got this answer?
Multiply 11 times 6 plus 10
Aha.
minus 19.
Okay. Well, okay, this is multiplication over here, by the way.
Oh, I'm sorry. I don't have my glasses.
Oh, no, you're fine. I'm sorry, I should have zoomed in.
thought it was like a
Did anybody get something else?
Okay, sorry. Let
No,
me
no,
do
you're
that
fine.
again.
I got 1,444.
1,444. Did anybody get something different from that?
I got 256.
256. Anything else?
Same, I got that too.
Okay.
I got 156.
156. Okay. Well, how can it be that we're getting different answers for something that, like, that, you know, if this made sense, if math made sense, which I promise you it does, we should all be getting some sort of consistent answer, right? We should all be getting the same thing. So whoever got 1,444, how did you get this answer? Or can you walk me through your process?
Yes, I did 11 times 6 was
Okay.
66, plus 10 was 76, times 19.
Right, and then this one I'm going to throw into the calculator because ain't nobody got time for that, right?
Right.
76 times 19, and we get 1,444.
But I'm guessing you're supposed to do the multiplication and then add them.
Yeah, something like
Okay.
that.
Okay, I'll start over.
For those of you who got the 256, that should have been our correct answer. I think. Let me go ahead and work that out. Because it turns out that if we're going to have consistent results among each other, that we have to have a consistent process for going through each operation. Okay. So it turns out that there is a correct order of operations that we have to follow. And that order of operations, at least for now, before I go into the exposition on that, is just going to be, we're going to take care of the multiplication before we take care of the addition. So I'll go ahead and multiply this times this and this times this. So this will be 66 and this will be 190. Then I'll bring down my addition add that together, and we should be getting 256 from that. This is actually the correct answer.
Is this PEMDAS?
You can interpret it as PEMDAS for sure,
Yeah, that's how I remember I learned it.
but I'm going to sort of put a slightly different spin on it, something that will be a little bit more flexible with some ambiguous cases or some more complicated problems. Okay, so the idea here is that we needed to get a consistent result among each other, where we can't dispute what the result is, we need to do the multiplication first. So the multiplication before the addition. Okay. So let me introduce you this order of operations. Some of you guys might have learned the order of operations as PEMDAS or PEMDAS. But the order of operations is just a phrase that mathematicians use to describe the order in which we need to resolve the operations in a numerical expression so that we, among each other, we can get the same answer. Okay. And I like to use the acronym GEMDAS. So this is the order in which we need to proceed through any mathematical problem if we're going to evaluate it, right? Get a single answer at the end. So the G here is not going to be the same as P. So if you've heard of PEMDAS before, PEMDAS starts with parentheses, but there's more than just parentheses in a given math problem. You might have brackets or other what we call grouping symbols. Okay. So the grouping symbols are going to include parentheses. So these guys. It's going to include brackets, which are the same as parentheses, but they're just these little square brackets. Another one you might see is braces. You don't see this nearly the same frequency. You don't see them as often as you see parentheses or brackets, but it's like these little curly grouping symbols. It turns out that roots are a grouping symbol, especially if you have an expression inside the grouping symbol. And then there's another symbol down here that we'll call the absolute value. And that's like if you have these vertical bars and you have some numerical expression in here. I'll highlight these pink. The vertical bars, the roots look like this zigzaggy thing. One other thing is fraction bars. Boom. So if I have x plus y on top of a fraction bar, and I have, let's call this w plus z on the bottom, then I can do the operations on top of the fraction bar independent of the stuff on the bottom of the fraction bar, and it won't change the result. So there's at least 1, 2, 3, 4, 5, 6 different kinds of grouping symbols that you need to be aware of because you're going to run into them in some of the more complicated problems. So we have to start with whatever's inside the grouping symbols first. As far as fraction bars, when I say inside the grouping symbols, I mean whatever's on top and whatever's on bottom. Once you've taken care of everything and done the problem inside the grouping symbols, you can move out to the exponents. After you're done with exponents, then you can take care of your multiplication. Then you can take care of your division once all the multiplication is done. And I'm going to fudge that here in a little bit. After multiplication and division is done, we can take care of our addition and subtraction. So you're not necessarily going to be moving from left to right, even though that's the way we read things, at least in the West. We're going to use this as our prioritization scheme for how we're going to tackle any of these problems. Start with grouping symbols, do all the exponents, do multiplication and division, do addition and subtraction. Okay. With multiplication and division, so this is a note for multiplication and division. You can do these from left to right. So if division comes first in a problem, we're going to take care of division. That is, if it appears on the left, we're going to go ahead and take care of that, and it won't change the result. And when we have only addition and subtraction, we're going to do these from left to right as well. Okay, I think I worded that a little bit weird, so let me just repeat that. If you ever come across a problem where you only have multiplication and division, you must do that from left to right. That's the only way you're going to get the correct answer. So sometimes division will come first, and you'll have to take care of the division first. Same goes with addition and subtraction. If we only have addition and subtraction left, but subtraction comes first on the left, then we'll just take care of that problem from left to right. But we have to clear all of this stuff in our head, in our like checklist, before we can get to multiplication, division, addition, subtraction. Okay. So let's do another problem. Let's look at this one. (73 minus 6 times 2 times 3). All right, so just take a moment to try to solve that one. Okay, does anybody have an answer for this one?
37.
37.
Am I hearing 37?
Yeah, I got 37
Yes.
too.
Okay. Anybody have something other than 37? Okay, so here we just need to go ahead and go through the multiplication first. Right, so in my head, I always write, I don't write down in my head, but in my head, I always say, okay, GEMDAS, to sort of guide me as to, my checklist. Do I have any grouping symbols? I don't have any parentheses, so I'm going to check that off my list. Don't have any exponents here, checking that off my list. I have multiplication, so I have to take care of the multiplication. So I have 6 times 2, or I could do 2 times 3. But I'm going to go ahead and just do the 6 times 2, do this from left to right. Like I said before, when we were talking about multiplication is commutative, so it doesn't matter what order you do this in. Okay, I could do 6 times 2, or I could do 3 times 2, or I could do 3 times 6. It's not going to change the result because of the commutative property. So this will be 12 times 3. I can go ahead and take care of that. That's going to be 36. And I'll just go ahead and bring down my 73 73 minus whatever this was. And then if you're doing this by hand and you really want to challenge yourself to not use the calculator, you can just stack this, right? We'd have to borrow here, so I'd have 13. So this would be 6 plus another one, which would be 7. I have a 6 left over, blah, 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 37. Okay. And if we're thinking about like what sign should this be, 73 is bigger than 36. So we should still be in the positive if we're thinking about money. So the answer here should be 37. Any questions about that one? Okay, let's level up a little bit. Let's think about 7/4 times 1/3 plus 4/5 times 1/2. I'm gonna give you guys a few minutes to try to work this one out. But if you have any questions, I'm right here. How are we doing here? Is anybody stuck? Like they're just at some impasse?
I just need more time.
Okay, yeah. Okay, does anybody have any questions? I'm going to go ahead and jump in and solve this one, okay? So the way you have to think about this is, again, our order of operations is prescribed by GEMDAS. We have no grouping symbols. We have no exponents. So we're just starting with multiplication and division if there is any of that. And we do have two multiplication problems here. So we'll have to take care of those separately. And when you're multiplying fractions, you don't have to worry about common denominators. If you're multiplying and dividing fractions, do not sweat it. Do not get common denominators. You don't need them. We're just multiplying straight across. So we have 7 over 12. And then over here, we should have 4 over 10. Okay, so we're adding those together. I think that what will ultimately end up simplifying your life a little bit is if you simplify the fractions where you can before proceeding with adding them. So what I would do here is once you get some fractions, you should simplify the fractions if possible. Right, you could do this at any stage in the order of operations because we're just going to be changing what the fraction looks like. We're not going to be changing the value. So it doesn't affect our order of operations. This guy right here, I can reduce to 2 over 5. So I'm going to go ahead and take care of that first. Maybe it helps, maybe it doesn't. Then what we could say here is we need to make these denominators match somehow. And the easiest way to do that, you could do the prime factorization, but I feel like some of you guys have some apprehension with it, so that's fine. As long as we reduce these fractions, what we can do is take this 5 and multiply it on this fraction. So I'm going to multiply this fraction by 5 over 5 and multiply this one by 12 over 12. Because remember, we're trying to match our denominators here. So now on the bottom of this denominator, we'll get 5 times 12, which is 60, right? Let me just check that real quick. Yeah, it's 60. And 5 times 12, which is 60 over here. So I'll have something over 60 plus something over 60. And that's that common denominator that we're looking for. So we have 5 times 7, which is 35. 2 times 12, which is 24. And we can go ahead and add that up. 24 and 35 is going to be a 9 and a 5 there, 59 over 60. And in my head, 59 is looking like a prime number. You can sort of guess at that if 59 is prime, because primes tend to be odd numbers. Now, that's not always the case. But if I try to divide it by something like 7, 59 divided by 11, I'm going to find out pretty quickly that 59 doesn't seem to be divisible by anything. So I won't be able to get a common factor and cancel that out between the 59 and the 60. So I'm just going to leave it alone for now. Did anybody get this out? Did anybody get something different from this? Or did anybody have any comments about the way they did it? Did they get there a different way? Did it take a little bit longer? Cool, cool, cool. Or 5 over 2 divided by 11 over 9 times 3 over 7. Okay, I'm going to give you guys about a minute or two to go ahead and solve that one. Okay. I'm going to jump in. This is the kind of problem that I really enjoy. Once you get comfortable with fractions, you'll see that these kind of problems are pretty straightforward. We're still going to use an order of operations because we have two operations here. So you might ask yourself or make a little to-do list, right? When you look at a problem like this, you have multiplication and division, but division is coming on the left, right? So we're going to start off our problem with division first, okay? So you might make a little checklist. We're going to do the division first. Then we'll do our multiplication. And if you make a plan first, at least that way, you know, when you show your work, if I see this plan written and I see a mistake in the plan, then I can sort of point to that and say like, okay, this is where you're making the mistake. So we'll take care of division first. And when you divide fractions, you need to keep switch flip. So I'll write this as 5/2 times 9/11 and take care of that first. So that's going to be 45/22. Then we can go ahead and drop down and multiply this by 3/7. You might ask yourself, can I reduce these before I multiply them? You totally can. It just so happens that in this case, nothing here reduces. So we're just going to leave it as it is and multiply straight across. So you might throw your calculator to the side and say 45 times 3 is 135. And then 22 times 7 is 154. And because we couldn't reduce that or simplify anything here, then we won't be able to simplify anything here. So even though the fraction has big numbers in it, it doesn't seem like it can be simplified. Does anybody have any questions here? Okay, let's take a look at this one. Six to the third power divided by 8 minus 5. I'll give you guys a few minutes to do that. Okay, so in this problem, GEMDAS is going to prescribe to us that we have to take care of exponents, then division, then finish up with the subtraction. So I'll go ahead and take care of 6 to the third power, which again, you should be interpreting as 6 times 6 times 6. Okay, so 36 times 6 is some number. Throwing that in the calculator just to get the 216. So we have 216 divided by 8 minus 5. So we've taken care of our exponents. We'll then fly through this division. Since we have our calculator handy, might as well try that. So 216 divided by 8 turns out to be 27. And then we'll subtract 5 from that and get 22. Questions, comments, or concerns on that problem? Does anybody get something different?
No, sir.
Awesome. Okay. What was that? 5? Let's look at 8 to the second power plus 10 to the second power divided by 2 to the second power.
Your screen disappeared for me.
Oh, interesting. Is it still blank?
No, I see it now.
Okay. And just to guide you on this, GEMDAS here is prescribing us to do exponents, then division, then addition. Anybody else get something different than 89? Okay. Let's maybe try one more. All right.
Can I ask something really quick? Can I ask something?
Sure.
When the the exponent is outside for the parenthesis, does that mean it's a multiplication or as an exponent for 10? I get confused.
Yeah, when the exponent is outside of the parentheses like this,
Uh-huh.
It's the same thing as if I didn't have the parentheses there. The
Oh.
exponent belongs to the number inside.
Oh, okay. Thank you.
Mhm. Okay, so looking at this without solving it, it looks like there's 5 steps. We got to start with rectifying the stuff that's in the grouping symbols. And then we'll move on to the exponents, proceed through the multiplication, the division, and then finally the addition. So when I say we have to like rectify or resolve whatever's in the grouping symbols, I mean that if you have more than one number inside a set of parentheses or brackets, we need to just do whatever's inside there first. So even though that this is subtraction, and subtraction should come later in the process, because we're inside the grouping symbol, we have to take care of that first. So this will be 3 times, this will be 8. And then I can rewrite the problem. Okay. So the only thing I've done here is the stuff in the grouping symbols to take care of that. Now I can take care of the exponents here, which 10 to the second power is 10 times 10, which is 100. So every time I do one of these steps, just, as a precaution, it might behoove you to just go ahead and rewrite the expression step by step, right? So I'm just going to rewrite everything that I have here. 3 times 8 was in the front. Okay. Now, as I said, I need to do the multiplication. And for some of you, it might not be clear, but whenever you have a number next to another number and they're separated by parentheses, that's one way that we indicate multiplication. So we need to be able to be comfortable with this, that this expression here says 3 times 8, which is going to be our 24. Then I can rewrite the problem. So I've taken care of the multiplication. Now I can take care of the division. And 24 divided by 4, if it were a positive, would just be 6. But I have a positive divided by a negative, so this will be negative 6 plus 100. And finally, I can take care of the addition. So if I had negative $6 in my bank account and I deposited 100, I should have $94, and that should put me back into the positive. So that should be the answer, 94. Okay. Does anybody have any questions about this last one? Okay, well, I apologize for the technical difficulties at the beginning of this, I was gonna say episode. I've been streaming too much on Netflix. At the beginning of this lecture, I think that on my end of things, I'll just restart my computer well before class time to make sure that the document camera is communicating with the computer. Aside from that, make sure that you guys are staying on top of the homework. I know that I sort of lectured you guys at the beginning of this with respect to being on top of your homework. Don't let it get away from you, because if you haven't at least peeked at your homework on fractions, or the second one on fractions 2, you will tend to get about 3 or 4 homework assignments throughout the week. We only meet twice a week. So you have to be putting in that work outside of our meeting times, um, because otherwise, it's going to feel like you're being inundated with information in the lecture, and it's going to feel like you're falling behind in the homework really quickly. So what I'm going to try to do next week is I'm going to open up so that over the weekend you could work on the first homework for this section R2 on resolving numerical expressions. So check MyLabs Plus here in a little bit for that to open up. That due date is going to be the same as the previous homework, so you'll have 3 due on Sunday, the 2 fractions, and then the 1 from today. We'll pick back up on this section talking about numerical expressions and expand it to talk about algebraic expressions next time. Did I miss anything? Do you guys have any questions for me about navigating Canvas or where you find certain things?
Sir, on the yes, I have one. On the
Okay.
homework where it says like score, where it says grade book score, that's where we scored, right?
Yeah, so if you're concerned about your homework grade, about every week or every 2 weeks, I will take your average homework grade from MyLabs Plus and import that or update it into Canvas. Canvas is going to be your official grade, so that's where you'll check there. MyLabs Plus is only going to report your homework average.
Okay. I already done one of them. I just have to do the other one. It's
Okay.
due by Sunday, right?
Yeah, they're due by Sunday. Gives you
Okay.
plenty of time to get into Math World or send me messages to ask questions.
Okay, thank you, sir.
Any other questions?
I have a question actually. Are we gonna have the lectures recorded on Canvas?
Yeah, so the lectures are recorded, like I already uploaded the ones from Monday. Unfortunately, on Monday, I accidentally hit the stop recording sort of in the middle of lecture, and then I started recording immediately after that. So it's split up into 2 recordings. But in Canvas, let me see if I can log on to Canvas real quick. Under Module 1, you will see a link that says Module 1 lecture videos. Okay. Oh yeah,
Where
change
can I find that? Because there's something called cloud recording. This is where I can find lectures, but I couldn't find anything.
Yeah, let me log into Canvas real quick. If you guys would just give me a minute. I am in. Now let me go ahead and share my screen. Okay. Okay, so this is what it looks like when you get into Canvas, right?
Mm-hmm.
I go ahead and click there. So we're in Math 1314. Our section is 247. And then this is the home page. Whatever I need to communicate to you is going to be located up here in the announcements. And I've only posted an announcement for day 1, but I'm going to post an announcement to remind you what is due by Sunday. So I'll post that after class. To get to the lecture videos or any of the materials in the modules, that is the material we're covering, you will click on modules here on the left-hand side. And once this loads, let's go ahead and we're in module 1 right now. If you look at the top of that module where it says module 1 lecture videos, you'll click there. And there's 2 links to YouTube videos because, like I said, last class I fudged it and I accidentally stopped recording and then started recording, so it's split into 2 videos. But you can click on this, it'll open up the YouTube thing, or you could click on the link. I think it might open up a new tab. In any case, that's the video, the recorded video of our lecture. After each class, I dump that stuff into YouTube. It takes about 30 minutes to an hour to process and for me to have the link uploaded. So I would say by about 4 or 5 o'clock, you should check back after the lecture, and those videos are going to be uploaded here, and you'll be able to scroll down. So this one says day 2 fraction arithmetic, if you need to go back and rewatch those. So after class today, I'll post something down here that says day 3, evaluating numerical expressions, and then the video will be posted.
Thank you.
Yeah.
Could you go back and show me how to get in the math world, virtual math world?
Yeah. So at any point when you're in our Canvas thing,
Mm-hmm.
Canvas page, you can go to the left over here
Right.
where it says virtual math world, and that should, when you click on that, it takes you to the Canvas page for virtual math world. Should redirect you there automatically, and you should see this thing.
Yep, I saw that.
Okay, so these are the hours for Math World here on the right. Math
Mhm.
Emporium is like the equivalent of Math World if you're taking classes at the Southwest campus, St. Philip Southwest campus. But in any case, those are the hours for Math World, 8 to 7:30, Monday through Thursday, and then Friday and Saturday, 8 to 2. If you keep scrolling down here, you see this table with instructors. Those are our tutors.
Right.
Our schedule, so when we're scheduled to be in our Zoom sessions for Math World, and then our meeting ID, which is the Zoom link, as well as the courses that we teach here. So if you scroll down just a little bit, Miguel, that's me. And I'm there Monday, Wednesday, Tuesday, Thursday, and Friday. So outside of class, there's plenty of availability, at least in the morning here and in the afternoon here, and also in the morning and afternoon here. And I tutor all of these courses, basically everything from elementary algebra, college algebra, all the way through calculus. But in any case, if you're looking for me specifically, you'll just click on this meeting link, and it'll open up your Zoom window, and then I will let you into the session and I'll be able to help you with your stuff. But if you're trying to get help outside of my hours, then that's when you'll want to like scroll through this and find a tutor that's available.
Right.
That, like Mike is a tutor for 13, 14 here. He has some availability that might be different from mine, right? So you might want
Right.
to find somebody else if I'm not available.
Okay.
Does anybody else have any questions about Math World? Okay.
Question about the My Math Lab or whatever it's
Yeah,
called.
My Labs Plus.
Okay, so when like I did my 2 assignments,
Mhm.
what if I just want to do it again, just keep it
This is-
fresh in my head so I don't forget?
Yeah. Let's see. What browser am I in? I'm in the Brave browser right now. So let me stop sharing real quick, and open up Google Chrome. Give me just 1 second. So My Labs Plus works best if you're in Google Chrome.
Right.
One of your classmates has already had an issue where My Labs Plus, for whatever reason, does not do well in Safari. So if you're working on a Mac, you might want to download Google Chrome.
Yeah, it worked fine for me. I just if I wanted to go in just to keep it fresh in my head.
Yeah. So let me go ahead and share my screen now that I have this open. Boom, boom, boom. This is what I want. And I'm going to go into My Labs Plus. You should see something that looks like this. It's not exactly the same, because this is sort of what it looks like on the instructor side of things once it loads. When you're accessing your homework, you go to the left-hand panel and click on Assignments. And once that's complete, you don't want to be messing with it. So what you'll do is you'll click on, I'm going to stop sharing real quick because let me click on it and make sure that when I click on Gradebook, it doesn't show anybody's grades. Okay, cool. Let me share this with you guys. Okay. So if you click on Gradebook, you'll see what you've completed here, and you'll see a button that says Review.
Okay.
So if it's like past the due date or you've already completed the homework, when you're in the gradebook and you're just reviewing the assignment, you can click on the questions. It'll open up a new, it'll open up the window like you're doing your homework, but it'll specifically say, any work you do here will not change your score.
Okay.
So you can continue working on the problems. It won't change your score.
Okay.
But just to get a little bit of practice.
So I go to Gradebook there. Okay.
Yeah. Alternatively, if it's before the due date, you can still access it through your assignments,
Right.
because it won't close. You'll just have to hit the similar question at the bottom of whichever question you want to rework.
Okay.
And if you get it wrong for whatever reason, it'll prompt you and ask you, do you want to keep the highest score? And so always keep the highest score.
Okay.
Yeah. Good question. So I feel like I've kept you for long enough. I'm going to try to make it so that next week and beyond, the lectures won't go much longer past 2 hours, because I know that this can be sort of exhausting to sort of sit through. It's exhausting for me to sort of speak through. But in the event that, you know, we have shorter class periods, I'll go ahead and post videos that will supplement what you're doing in MyLabs Plus so that you can have those as references as well. If you have any questions, you're more than welcome to hang back or send me a message in Canvas or in Remind. I'm very good about responding to the Remind messages. But if you don't have any questions, you guys are free to go.
Thank you.
I have a question.
Have a good day, everyone.